Welcome once again to your TV library. Today we're going to be looking at Lavoisier and his work with energy and the discovery of oxygen and its use for combustion. Anton Laurent de Lavoisier was born in Paris in 1743 to an affluent bank clerk family. From a young age, he was interested in nature and he often carried out barometrical and meteorological observations. Young Lavoisier was also interested in botany, geology and mineralogy and attended some chemistry courses. Persuaded by his father, he took up law studies at the University of Paris and obtained his bachelor's degree in 1763. It was likely due to his studies in law that his works were so well written and that they were always comprehensible, well-defined and logical. During his law studies, young Lavoisier was also attending lectures on the natural sciences. In particular, he was enthusiastic about geology and mineralogy. It was shortly after his graduation in 1764 that he began his apprenticeship in the Parisian Parliament. He was open-minded and curious about everything that surrounded him. Not giving up on his interests, he devoted himself to geology, physics and chemistry, which resulted in his first publication in chemistry in 1764. At the age of 24, he was chosen to become a member of the French Academy of Science, and it was there that he wrote about the origin of chemical elements and combustion. The daily life of Lavoisier was focused entirely on science. Lavoisier's versatility and his legal studies led him to take an interest in politics. He even became a tax collector, employed by a private company at 26 years of age. While working for the government, he developed a new system of measures which aimed at the standardization of scale for all of France. However, it was not politics, but chemistry which brought him significant fame. Lavoisier's experiments were some of the first that could be characterized as quantitative research. He demonstrated that even though matter changed its states in chemical reactions, the overall mass of reactants and products remained equal from the beginning of the reaction to its end. His experiments provided the basis for formulating the law of conservation of mass. And in 1786, Lavoisier advocated that the caloric theory would replace the phlogiston theory. Due to Lavoisier's research, it was possible to establish that food was oxidized after being eaten. Oh, excuse me. As a result of that process, heat was produced simultaneously, which Lavoisier and Laplace measured using the calorimeter. Lavoisier was an activist and was deeply convinced of the need for social reform in France. He was a member of the community in favour of tax reforms and new economic strategies. During the French Revolution, he published a report on the financial situation of France. It was shortly afterwards that he was called a traitor by the revolutionists for being a tax collector. For his strong political and economic views, he was sentenced to death. Prior to his execution, he asked the judge for permission to complete his scientific research first. However, the judge's reply was, "The Republic needs neither scientists nor chemists. The course of justice cannot be delayed." He was guillotined in Paris on May the 8th, 1794, and later buried in the cemetery in Arancis. So now that we've learned a little bit about the life of Lavoisier, let's look to his lifetime of achievements. To his work with energy and the discovery of oxygen and its use for combustion. Lavoisier focused his work on heat and combustion. The definition of heat was still driven by the ideas of phlogiston theory, although this theory was subsequently abandoned by Lavoisier's time and he himself contributed a major part to this scientific revolution. Lavoisier strongly believed in the fact that mass is conserved in chemical reactions, an idea originating from the scientific endeavours of the Enlightenment. The idea of mass conservation was the key to one of the most important findings in chemistry, oxidization. Lavoisier realised that when a metal became rusty, the mass of the calcified metal, calx, usually weighed in powder form, had a greater weight than the metal which was initially available. Lavoisier also found that the process could be reversed. For example, when the calx was reduced to the metal by heating, its weight decreased. The phlogiston theory couldn't explain these changes of masses because heat was an imponderable or weightless element. Lavoisier developed the idea that air might be the key to the changes in mass and aligned his experiments to this theory. The theory of combustion could not be developed until Lavoisier and Priestley, a British chemist, combined their respective scientific findings. They had a mutual respect for one another despite having different opinions on what combustion could be. Priestley's views were strongly related to the phlogiston theory, but he controlled his experimental environment better than the Frenchman did. Priestley was very alert to the fact that the air produced during an experiment was different from normal air. Lavoisier reconducted an experiment, heating common red precipitate of mercury, just like Priestley had done before, with enhanced attention to the gas produced in the process and analysed it. The difference between the experimental gas and fresh air was the last clue he needed. He found the element involved in the calcification process and called it oxygen, referring to the Greek words for making something sharp, easily interpreted as acid producer because of its sour tastes of acid. Although Priestley had conducted the same experiment, he did not identify elementary oxygen. Instead, he characterised the gas produced as dephlogistated air, strictly following the phlogiston theory. Lavoisier used his newly found knowledge to include oxygen as part of a chemical reaction and was able to extend his theory of the effects of calcination and combustion.